Here are solutions to homework set number 1 for ECE 463-663 Modern Control. The first homework set looks at LaPlace transforms and dominant poles. So the first problem is name that system. Given a transfer function, I can find the step response. Going backwards, given the step response, find the transfer function. Well, for this one, it looks like a first order system, and I know that because there's no oscillations. So I know the answer is going to look like A over S plus B. I need to get two pieces of information from the graph. One would be the settling time. It's right about here, about 1.5 seconds, ballpark. So I know that B is 4 over 1.5. To get A, I can plug in S equals 0. That gives you the DC gain. DC gain is about 1.65-ish, something like that. That gives me my second equation, A over B is 1.65. So putting them together, B is 2.667, A is 4.40, so here's roughly the transfer function. And note that I get a first order system. This is actually a second order system, and I know that because for first order system this takes off right away. This one kind of starts out sluggish, then picks up. There's a second pole, a fast pole, but it's really hard to see. Within about 0.05 seconds, the fast pole's gone. So I know there's a dominant pole. The fast one's really hard to see. That's kind of why it's called a dominant pole. It dominates the response. That's problem number 1. Problem 2 is if I have oscillations. What oscillations tell you is that this is a second order system. I've got a complex pole and its conjugate. So it's going to be S plus B plus minus JC in the denominator, and a term in the numerator. I need to get 3 pieces of information from this graph. One way to do that is to say that the real part of the pole is this envelope, that exponential envelope that's decaying. It looks like it settles out right around here-ish. Kind of hard to say. If I say that's about 2.4 seconds, ballpark, then I know that B, the real part of the pole, is 4 over the settling time, 2.4 seconds. To get the complex part, that's the frequency of oscillation. So here's the minimum, here's the first minimum, second minimum. It's kind of a trade-off. The further out I go, the better resolution I have in time, but a little bit harder to see the flat part of that curve. So 3 oscillations, I really can't see 3. I took right here. I know that C is the frequency in hertz. I've got 2 cycles in about 2.4 seconds. That's in hertz. Anything English is wrong. So I've got to multiply by 2 pi to get to radians per second. That's the complex part of the pole. Then to get A, find the DC gain. Plug in S equals 0. And the DC gain is right here, about 1.85. So go through those calculations. Here's the real part of the pole, about 1.6. The complex part is about 5.02. And the DC gain, A is whatever it takes to set the DC gain, 50. So here's my transfer function. And again, that picks out the dominant pole. If they're fast poles, they're really hard to see. They're going to appear in this part of the graph. There's just not a lot of data there. Problem 3. If I have a transfer function that represents a differential equation. To find that differential equation, cross-multiply, multiply out the polynomials, and the basic assumption of LaPlace transforms is everything's in the form of e to the st. So when I take the derivative, I get s e to the st. So multiplying by s corresponds to differentiation. So this would be the third derivative of y, the second derivative of y, first derivative in y, first derivative of x. So there's the differential equation that corresponds to that transfer function. And you kind of see it by inspection. The denominator polynomial is the differential equation in terms of y. The numerator polynomial is the differential equation in terms of x. Now the reason we do that is it makes solving problems a whole lot easier. If my input is a sine wave, I know that my output's a sine wave. What I don't know is the amplitude and phase shift, or the sine and cosine terms. To determine that, I use phasor analysis. So here the frequency is 6 radians per second, so s equals j6. Again, Laplace transforms assumes everything's in the form of e to the st. From Euler's identity, if I have e to the j6t, I have a cosine term and a sine term. So s equals j6 to give me the cosine and sine of 6t. The input is 4 minus j2 in phasors. The real part is cosine minus j is sine. This is the gain everywhere, my transfer function. Plug in what's the gain at this frequency. Again, this is the gain everywhere. All I care about is the gain at 6 radians per second. Times the input at 6 radians per second gives me a complex number. What that means is the real part is cosine minus j is sine. So there's my answer. Number 5. If my input is a unit step, looking like this, that's where you need to use Laplace transforms. Now this is the transfer function. Take the Laplace transform of x, that's 1 over s, multiply the two together, and that's the Laplace transform of y. To find y of t, take the inverse Laplace transform, and to do that I'll do partial fraction expansion. The way I find that is use the cover-up method to find the first term. Well, I know the answer is going to have something over s plus 2, s plus 8, s plus 9. To find the first term, cover up this guy, analyze at s equals 0, I get 1.67. To get the second term, I cover up this term, analyze at s equals minus 2, and I get 3.8095. And likewise at plus 8, plus 9. Take the inverse Laplace transform. This is 1.67, 3.8, e to the minus 2t, 13.3, e to the minus 8t, minus 17.1, e to the minus 9t for time positive. And the last one is find a first-order approximation for this third-order system. To do that, I keep the dominant pole. That's the pole closest to the origin, so I know this is going to be something over s plus 2. Pick A to match the gain somewhere, typically DC. So the system, my third-order system, has a DC gain of 1.67. Pick A to make the first-order system also have a gain of 1.67. So I get the third-order system behaves almost like the first-order system. The point behind that is kind of the whole idea of modeling. I want a simple model, but I want an accurate model. I'd rather try to analyze a first-order system than a 200th order system. To do that, you keep the dominant pole. In this case, keep the dominant 1. Other systems might keep the slowest 3 or 4. Depends how good you want the model to be. In this case, if I treat this as a first-order model, these two should behave about the same. If it's the same system, they've got the same frequency response. If it's the same system, they've got the same step response. So checking in MATLAB, here's my third-order system. I use ZPK. I've got a 0 at minus 6, poles at minus 2, minus 8, minus 9, gain out in front of 40. Here's my first-order system. No zeros, pole at minus 2, gain at 3.33. Plot the step response from 0 to 4 seconds. Again, I chose 4 seconds. The 2% settling time is 4 over 2, 2 seconds. Double that is what I kind of like doing. So you see, here's the 2% settling time, then steady state. Find the step response at the third-order system, find the step response at the first-order system, plot the two together, and they kind of look alike. About the same settling time, same shape, same DC gain, almost the same system. Yeah, not exact. What that means is that if I design a system, assuming this is the correct plant, and then apply the third-order system, it will probably work. There's an extra delay that I'm not accounting for, but the two are very similar. Kind of a sidelight. I can come up with a better model if I add 80 millisecond delay. Then here's the first order system with an 80-second millisecond delay in red. The third order system, that's a much better model. So sometimes I'll do this. I'll treat my third order system as a first order system plus a delay. And the delay kind of models all the poles that I ignored. That's one source of delays. Sometimes we do that, I get a better model. Sometimes we don't. In this class, we really don't because I want to put this in state space form, and delays don't convert to state space form very well. So you can do it, but oftentimes you just ignore it and say the model's going to be a little bit wrong. So that's why you actually use simulations like MATLAB to test it when you do have a delay. Does your control law actually work with the actual system? That's homework set number 1 for ECE 463 Modern Control.